Hello, right, this is the second video in NACHO chemistry in the series, and this is for foundation and higher students. So you can all look at bonding. Okay, so let's have a look. The first video was about the periodic table and structure, but now we're going to have a look at bonding and how we put all of these chemicals together in order to make all the different molecules and compounds that we see all around us. So first of all, there's three types of bonding. There's ionic bonding, which is between a metal and a non-metal. And if you remember the stairway to Devon, that means a chemical from on the left joined with a chemical from on the right of the periodic table. Covalent bonding between non-metals, so that's between any chemicals over on the right-hand side of the stairway to Devon. And then metallic bonding, which is just how metal particles bond together, and we'll have a look at the structure for that. Okay, so let's have a look at ionic bonding first of all. As I said, ionic bonding is on the periodic table, any chemical on the left bonded with any chemical on the right. In this case, the electrons are given away or transferred. Don't ever say they are shared, because you will not get the mark, because that is for covalent bonding. So electrons are transferred from one chemical to another. It's usually from the chemical with the least electrons in the first place will give it away to the ones with the most. And then when we say the electrons have transferred, then ions have been formed. And this word ion just means charged particles. So if you see ionisation, that is just the process of charging particles. If you see ionic bonding, that means making charged particles through bonding them together. So let's have a look then at some examples of ionic bonds. Now these are some of the common examples that you will see, and you may well be asked to draw them. First of all, you will notice that they are drawn with dots and crosses. And the reason for that is just so that the examiner can see that you understand that electrons have transferred from one chemical to another. So let's have a look at sodium and chlorine to start with. Now you'll notice chlorine, when it's on its own, is an ine, but when it joins together with another chemical becomes an ide. And that's what happens with group 7. So fluorine will become fluoride when it's joined together with another chemical. Now you should be able to talk about these chemicals and say that sodium's in group 1 and chlorine is in group 7. So straight away you should know that there's 1 electron in the outer shell of sodium and there's 7 in the outer shell of chlorine, because it's in group 7. And so it's easy to take 1 electron and give it away from sodium over to chlorine. And you can see there, I've just represented the electrons across and it's gone over to there. They've been put into brackets to show that it's an ionic bond. And the last thing, and this is absolutely crucial, is this here, and it's the charge. So this has become positive and this one's become negative. Now there's two ways you can think about this. You can either think, okay, so sodium has give an electron away. So in my mind, that's a minus, but it's not, it's the opposite, it's a positive. Well, the real reason for it is that sodium started off with 11 electrons and 11 protons, which cancel each other out. But because we've lost a negative, it means I've now got one more positive proton. So it means my particle has become charged as a positive. This one has gained a negative electron, so has become negative. So that's sodium chlorine becomes sodium chloride. This is exactly the same as the previous one, because you've got a group 1 element, lithium, and you've got a group 7 element, fluorine, to make lithium fluoride. Again, 1 electron from the outer shell has travelled over and transferred over to fluorine to make it lithium fluoride. Again, the charge, it's only given 1 electron away, so this has become positive and this one's become negative. This one then, because the whole point of ionic bonding is we want to get a full outer shell of 8 electrons. So this one then is a group 2 and a group 6 element. So you can see you've got magnesium, which is in group 2, and you've got oxygen, which is in group 6. So that means magnesium have got 2 electrons in its outer shell to give away, and oxygen can take 2. So 2 electrons transfer over, and in this cross it was red dots that have transferred over, but the charge this time you'll see is 2 plus, because this one has lost 2 negative electrons, so it's got 2 more positive protons and becomes 2 plus. This one, however, has gained 2 negative electrons and so has become 2 negative. So again, group 2 and group 6 love each other. And then the last one, and this one I'd say probably is about as hard as it gets. Sodium plus oxygen. Well, you'll notice oxygen's in group 6, so it can take 2 electrons. Oxygen's in group 6, yeah. Sodium is in group 1, so sodium has got 1 electron each in their outer shell. So you can see that oxygen can take 2, and then that means I need 2 sodiums to fill it up. So now I've got a full up oxygen here and a full sodium here because it's lost its electron from its outer shell. However, look at the charges. This one's only lost 1, so it's become a positive, and that's become a positive because they've only lost 1 each. But this one on its own has gained 2. Oxygen has gained 2 electrons, so it becomes 2 negative. Okay, so if we look then at some of the giant structures of ionic compounds, there's some certain rules you need to remember. They're held together by strong forces of attraction. They have high melting and boiling points. They do not conduct electricity when solid, but they do conduct electricity when molten or liquefied by heat or in a solution. So if you think about table salt, as a solid, doesn't conduct, but yet when it's heated up, it does conduct, and that's because the electrons have become free. Okay, so covalent bonding, a second type. This is between metals and non-metals. And remember I said between the chemicals on the left and the chemicals on the right of the Stairway to Devon. This time they share electrons to make sure they've both got a full outer shell. Same, again, using dots and crosses to represent the electrons. So examples of covalent bonding. You'll see these are some of the easier ones, H2, Cl2, O2. And the whole point is hydrogen has only got 1 shell, and it's got 1 electron in its outer shell, but the first shell always fills up to 2. So you will never find hydrogen on its own. It always goes in pairs, it's diatomic. So you'll see that they share an electron each, so they are both full. Oxygen, sorry, let's just go back one, sorry. Oxygen, this time they share 2 each to make sure they're full, and chlorine just shares 1. Now if we look at these are a little bit more complicated. Methane, CH4, well, carbon has got 4 electrons in its outer shell, which means it can take 4 electrons to fill it up. If I've got 4 hydrogens, that means each of those will share their 1 electron in their outer shell with the carbon, and if you look and count the outer shell, you'll see that 8 are there to fill it up. Ammonia, NH3, same principle. Nitrogen has got 5 in its outer shell, so it can take 3. So it has 3 hydrogens attached onto it. Water, again, I think if you turn that round, you'll actually see it looks like, I think it looks like Mickey Mouse and its ears sticking up. It's upside down at the minute. So you can see then that hydrogen again, H2O, each give an electron each to oxygen to fill it up. Now I think this is probably the most complicated one you'll come across, and that's carbon dioxide, because it's really difficult to see, especially here, how many electrons they're sharing. Now carbon only has 4 in its outer shell in the first place, and oxygen has 6. So oxygen needs 2 and carbon needs 4, and this oxygen needs 2. So if you think about it, this oxygen needs 2, it will share 2 from this carbon, and it will share 2 from this carbon. Whereas oxygen will then share 2 of its electrons with the carbon, and 2 from this side. And if you actually count all the electrons, it actually fills up quite nicely. So it's eight in each, but that is as difficult as it gets. So let's just have a look at the giant covalent structures for covalent bonds. Now these are the ones you're more likely to come across: diamond and graphite, which are both carbon structures, and then silica. They are all atoms linked by strong covalent bonds. These bonds must be broken for the substance to melt or boil, hence the reason they have high melting and boiling points. Okay, so let's look at the last type of bonding then, and that's metallic bonding. It occurs in metallic elements such as iron and copper, and basically the transition metals. Also occurs in alloys such as stainless steel, and an alloy is a mix of materials where one is usually a metal. So a metallic bond is the attraction between the positive ions and the delocalised negatively charged electrons. So what you need to draw. This is usually a 2-mark exam question, at least, sometimes 3, where they ask you to draw a metallic bond, and you literally just draw as if you were doing drawing a solid with the particles all neatly lined up and touching each other, but you make sure you identify that they are positive metal ions, and in between the metal ions you've got these free electrons, and that's the reason that metals conduct electricity, because of those free electrons in the first place. So going back then, overall we today have looked at the 3 types of bonding, and if you learn the examples that we've given you here, that will cover most of the questions that you could possibly be asked to draw, and they do ask you to draw them in exams, and you would be expected to make sure you do dots and crosses and show exactly whether it's a covalent or an ionic bond. Thank you.